Hi everyone, let's talk about why fractions have a unique reduced form. Let's say we're looking at the fraction 3 over 9. We know that we can reduce it to 1 over 3, and this is also something that can be written as negative 1 over negative 3. So we call this one the unique reduced form because GCD of 1 and 3 is equal to 1 and 3 is positive. So we're going to be proving that there always exists a reduced form. We're going to be proving that it's unique. And we're going to be looking at the relationship between the unique reduced form that exists and the rest of the forms. So in a sense, it'll turn out that the reduced form generates the rest of them. But we'll look at that at the very end. So let's show existence first. This one is not too bad. Let's say R is a rational number. Then by definition, R is equal to S over T for some integers S and T. And since S over T is, well, also we're assuming that R is not 0 because weird things happen when R is equal to 0. So S over T is equal to negative S over negative T. So we can assume without loss of generality that T is greater than 0, because if it's not, we can just take the negative of both the top and the bottom. And what we're going to do is that we're going to write it like this. R is equal to S over T, and that is equal to S over the GCD of S and T divided by T over the GCD of S and T. And we know that the GCD of S over ST, GCD ST, and T over GCD ST is equal to 1. This is a standard result. So this proves the existence of a reduced form. Now we want to prove uniqueness. And we're going to need Gauss's divisibility lemma for this. So if you haven't heard of it, please check out the other video on Gauss's divisibility lemma and Euclid's lemma. Alright, so what we're going to be starting off with is the idea that R is equal to A over B, a reduced form A over B, and a reduced form alpha over beta. So AB, GCD of A and B is equal to GCD of alpha and beta is equal to 1. And we're going to be assuming that B and beta are both positive. So we can write this as A beta is equal to B alpha. And this means that beta divides B alpha and B divides A beta, but beta and alpha have a GCD of 1. So by Gauss's divisibility lemma, this implies that beta divides B, and B and A have a GCD of 1. So that means B divides beta. And together, since they're both positive, this means B equals to beta. And since B equals to beta, we get that A equals to alpha as well. So this proves the uniqueness of the reduced form. So once again, what we used is called Gauss's divisibility lemma. And finally, we're going to talk about generation. So suppose R is equal to A over B is equal to C over D. And we're just going to assume that GCD of A and B is equal to 1. And that A is not 0. So we're not dealing with R is not 0 equivalently. So we're going to write this as AD is equal to BC. And that's going to mean that A divides BC. And by Gauss's divisibility lemma, again, since AB is equal to 1, this is going to mean that A divides C. And we also get that by definition that there exists an integer k such that AK is equal to C. So we can substitute that into this to get AD is equal to BAK. And since A is not 0, we find that we can cancel out the A's and get D is equal to BK. So what that means is that C is equal to AK and D is equal to BK. So R is equal to A over B, which is equal to C over D, and that means this is just AK over BK. It means that the unique reduced form, it generates all other forms in which R can be represented by just multiplying the top by K and the bottom by K for some non-zero integer K. Thanks for watching, and I'll see you next time.